Hello, everybody. So we're going to do an example here where we want to do a design. And the first part we're going to start off with is imagine that we had this state graph. Now, where this state graph comes from at the moment, I'm not going to worry about. Just assume we have a state graph. It was given to us and somebody said, hey, I want you to implement this state graph. Now, let's kind of walk through what this state graph says. I don't have any outputs listed here. Right now, I just want to worry about how to get the basic transitions. Doing outputs is a really simple aspect of this. So right now, let's just assume that we want to implement the state transitions so that we have the basic function of this table and we can worry about outputs um, based on what we have available here. It's a fairly simple addition. Very often we name our states. I've given my states names A, B, C, and D because they fit nicely inside the graph here. Um, when you're doing simple design, that's often what you will do. And you'll sometimes have fancier names, but you'll then have kind of like abbreviated labels so you can draw charts. Um, Good variable names and even more meaningful state names often don't fit unless you have a lot of room when you're drawing. So kind of like good first sketches, you'll do simple stuff like this. All right. And we do these names because you don't necessarily know how many states you want and how many bits and all the rest of this type of game. And sometimes you've discovered, oh, it would have been so much better if I had named this other state zero or, however. So there are different ways to reassign the values. There's nothing magic about which one of these gets numbered 0 and 1 and so on. Um, there's different schemes. So rather than have to worry about that, we just give them, letter names at first. And you can see for state A, it's going to stay at A whenever I get an input of 0, and A will transition to B whenever I get an input of 1. I stay at B on a 1, and I transition from B to C when I get a 0. C on a 0, I go to D. C on a 1, I would go to A. D on a 0, I stay at D. D at a 1, I go to C. Now, ignore the numbers on the side because I'm going to just kind of number them, the states in the most obvious way in a sec. Um, but initially, let's just take a look. When I'm at state A, everything that I've got inside this graph, I want to put inside the table, which means I need to label my states A, B, C, D. So I know, okay, there's 4 of them. I have inputs. I can only have two things, 0 or 1. You can see from each one of these states, I either have a 0 or a 1. So that gives me the state and the input. So I've got A can have a 0, 1, B can have a 0, 1, so on and so forth. My next state, again, ignore the numbers here for a sec. We'll get to that in a moment. Um, A on a 0, A on a 0 goes to A. You can see it inside the graph. And so my next state says A. A on a 1, I get a 1, I go to B. So I put in B. Right, you can see B on a 1 goes to B, so B on a 1 goes to B, but B on a 0, right, B on a 0 goes to C. You can see B on a 0 goes to C. C on a 0 goes to D, and you can see that in the graph. And C on a 1 goes to A, so C, when I get a 1, goes to A. D on a 0, D on a 0 goes back to D, goes back to D. D on a 1 goes to C. D on a 1 goes to a C. So this table summarizes everything that's in here other than the particular way I drew the pictures. So the one thing the graph adds is it's very pictorial, so you can kind of see the state flows. All that information is in the table. It's not very pictorial. So if you looked at these letter combos, you're not going to get, oh, wow, there's this kind of nice little looping structure that's going on here. So, there's a reason for each of these. The graphs are there to help human beings visualize what's going on. Most of us find the graphs more appealing. We can kind of see what's happening. Um, you know, but the tables are going to be much better when we go to do a lot of the design aspects. So, particularly if you have to go down to kind of like a gate style, which we'll do in a sec here. Um, when you have to go to the gate styles, then we're going to want to very much so do a state table. So let's assume we are going to go, now that we've shown we go from a graph to the state table. I'm going to assign state numbers now. So that's why I just say, okay, A, B, C, D. I have no better reason to pick them. I look at the graphs and I go, well, A, B, C, nice sequence of numbers. D's on its little side loop next to C. So I just determine, okay, I'm just going to number them in sequence. So A gets 0, B is state 1, C is state 2, and D is state 3. So then I just put those same numbers, right? A is 0, B is 1, C is 2, B is 1, D is 3, A is 0, D is 3, C is 2. I just put those next to them. Then you can kind of imagine I'll ignore the letters when I go to do a design. Now we're about to do, let's say we want to do an implementation of this. So maybe I want to do this by cardinal maps. So then I would have state 0, 0. So this would make a table then, right? 0, 0, 0 is the first row, 0, 0, 1, 0, 1, 0, 0, 1, 1. If you look by having the gaps and everything in here, it's almost nicely set up for a Mux design. We're going to do a Cardinal map here, and we'll put these 2 bits along the top line of it, and we'll put that one on the side rows. But you can nicely set up. Now, since I have 2 next states, I'm going to have to do 1 column at a time. So this is my state bit 0 is the right-hand column, and state bit 1 is the other. So I'm going to have to do a Carnot map for state bit 0, and I'll have to do a different Carnot map for state bit 1. So however many state bits you have, that's how many Carnot maps you're going to have to do. And we'll show you, the first one we'll do here in this video will be this, and then we'll implement some other ways um, in a sec here. All right. So let's take a look at the state. So I've taken state bit 0. So let me actually, so I'm flipping between my 2 ones. If you look at state bit 0, right, it's 0, 1, 0, 1. It's kind of a nice pattern. And then 1, 0, 1, 0. It's easy to remember. 0, 1, 0, 1, 1, 0, 1, 0. All right. So when we come in here, when I'm doing the next state bit 0, I've got 0, 1, 0, 1, 1, 0, 1, 0. So just walking through the Carnot map, you can see I've got my state bit set, most significant, then the least significant state bit. So I'm using capital S for my state, and I usually, just to make it easier to see and tell what my state bits are, I put these little kind of serifs on the end of them. You don't have to do it. It just, to me, when I look at it, I go, oh, that's a state bit. Just makes my life easy. Um, so I've got, I just number as the subscripts, the order of them. So that's the left, state bit 1, state bit 0, the right, the least significant. And then my inputs, like I said, are on the vertical part, handling which number of the rows. So you can just see it's set up. Now, this is the design for the next value of state bit 0. And I do this kind of little sub n first. Some people do next underscore. I've seen a lot of conventions, um, you know, but that's what I tend to do for these. Now, the reason I do that is we go back to remembering um, when we first started out, I said we had for all of our sequential designs, we had a state section. You can see this in this little upper right hand thing diagram I have here. We have a little square box with state in it. That's all my registers. And what comes out is the current state. And that goes into the next state logic, which is a combinational circuit. And so I can't have it come out as S. I have to give it another name, but it's connected to it. So, um, you know, next underscore is a good way to do it, or N of them. If you use a little N first as negation, then maybe you want to say next underscore or something, or N underscore, whatever works. just to keep them nice and distinct. Um, since I tend to put these serifs on it, when I see that N, I don't think negation. I just think, oh, next state. So to me, that's the other reason I do that kind of serifs. It distinguishes it. All right. So that's anyway the basic setup for how I have this. So that distinguishes the wires. The wires coming out from the state have the name state on, and then N state is the ones that are coming into the state out from the next state logic. So I'm designing what's going to come into the state. I'm at this point, since I'm just doing generic memory, that means I'm doing D flip-flops. So therefore, I don't need to worry about anything else. Um, all right, now I could look at this. So we've just explained where the first table came from and why the naming conventions and everything. We'd already copied this one in, right? Remember, it was 0, 1, 0, 1, 1, 0. Don't forget, you have to go to the outside, the far column, 1, 0, because this is, um, set up in that gray code style order. I could just look at this and recognize, oh, I've got, this kind of checkerboard pattern, right? Zeros, ones, zeros. Whenever you see that checkerboard pattern, you go, that's an exclusive OR. You notice that um, there's a split when S1 changes, there's a split when input changes, no split when S0 changes. That's why there's a double zero, a double one, things like that. That means S0 is not involved. You just go, oh, next state 0 is just the current state 1, exclusive or input. You can just look at it and recognize it. If you don't recognize it, so that's a great way to find it quick. But if you don't recognize it, you can just do your encirclements. Um, if you do your encirclements, you can encircle the upper right hand encirclement. Those two ones will give you the term not in and S1. And when you circle the lower left hand corner, you'll get in and not S1. Boom. So you'll see next state 0 is also equal to in prime and S1 or in and S1 prime. And that gives you your basic design. Now, when you go to the next state 1, let's go back to the previous one so we have our table. When we look at the next state, state 1, that's the left bit, a little more complicated pattern, 0, 0, 1, 0, 1, 0, 1, 1. When we come in to then fill out the table, we have 0, 0, 1, 0, 1, 0 on the far side, remember gray code, and then 1, 1 down the middle. Well, our encirclements, you'll see it's kind of ugly, but there's 3 encirclements, a left one, a right one, and then the up down on the middle. Could be worse. So there's not a nice pretty pattern on that for picking XORs or things of that sort. So we just got to kind of take what we've got. So we end up with 3 encirclements. So if I grab the first one here on the left, I'll have it's on top, so it's in prime, and then it's where S0 is, so I get in prime and S0. That's the first term. And then the up down in the middle, right? That's state 1 and state 0. You'll see my second term is state 0 and state 1 there. And then my last one is this upper right encirclement, which is under state 1 and not in. So in prime and state 1. So that gets me my design. So now I've got these Carnot maps. I know what the next state is, right? And since I know what the next state is, this part on the right here that shows the logic, that is the next state logic. So N0 or NS0, that's the wire, and it was generated from this logic, right? In prime and S1 or in S1 prime. So that is the next state logic for it. And it took the states in, which came from the previous state. So really described in these equations, right? Next state 0, next state 1 is actually that whole combinational logic. The upper part's a flip-flop. So I really have a complete description of my equations right here. So it's just ready to implement. So that's what we'll take a look at when we go to the code inside of Verilog. So I'm going to have you do the code in Verilog. I've actually um, have a nice tool that you'll be able to use that if you follow the link, it'll actually pull up the code that I have written. So therefore, we can kind of just walk through it together. We'll do that in a separate video because we've kind of, I think, exhausted time out for this. I don't want these to be too long. Um, but I do want you to remember these equations because these equations that we generated here are what we're going to implement there. And I'm just going to, in that video, say, hey, remember that previous video? We designed this, and away we go. Um, there will be other ones that we're going to do where I'm going to say, hey, remember we had the state. So this state table is also very important to us. So for the state table, um, we're going to be able to do some other designs right from this state table. So you might want to refer back to this one as well. Um, anyway, that should give you enough to make the coding examples make complete sense. So hopefully this helps, and I'll see you in the coding example videos.